Hello class, so this is CSE 5250, Section 2, Week 9. We're already past the midpoint for the semester, and from there, it's already October, and suddenly it's just gonna be the end of the semester. So, stay tuned, we're gonna look at more applications of parallel programming. For this presentation, I'm just gonna talk about a little bit of the theory behind parallel computing and how that stacks up with what we know about sequential computing. So let's begin with that. Right, so we already have pretty good descriptions for describing sequential computation. We have the lambda calculus, we have the Turing machine, we have the von Neumann architecture, and it turns out they're all equivalent to one another. So we can say that anything that can do computation, if it can simulate the and, or, and not gate, you basically have something that can simulate a Turing machine, and we say it's Turing complete. Or rather, it's Turing equivalent. So yeah, we have pretty good descriptions on how sequential computation works. We already know what its limits are. It's a well-studied topic. We can determine whether a Turing machine halts given a finite string of input symbols. And it's actually pretty simple. If you want to determine whether a Turing machine halts given an input of limited size, simply just feed it every possible combination of input symbols, every possible sequence of input symbols, if I may correct myself. And if there is one, even just one input that halts the Turing machine, you've answered your question. We have limitations with the Turing machine, such as, can we find an algorithm that can determine whether a program halts in general? Or put another way, is there such thing as an infinite loop detector? The answer is no. Yeah, there's two main proofs for why we can't have a program that can detect an infinite loop. The first proof involves feeding a copy of a program that supposedly detects an infinite loop into itself, and then causing a paradox that can only be resolved by saying, "Oh wait, we can't have this program in the beginning, in the first place." There's another proof that involves Cantor's diagonal argument, which is a bit mind-melting in the sense that that same proof is also used to prove that there are two sizes of infinity. But that's enough of a tangent right now. So, do we have anything for parallel computing? Well, not in the general case, but we do have models we have models and descriptions for specific setups of parallel computing, and I'll be getting into that a little bit. But first, how were we writing parallel code? Well, there are two main ways of doing this. One is to have the compiler, or the interpreter, do that all for us. So the idea is, if the compiler can recognize blocks of code that don't depend on one another, when that compiled program executes, the program will basically just run those blocks all at the same time. The second option is we have to sit down, think about it, and we write it all ourselves. This is what we did with the MPI program. We had to manually write a parallelized for loop by dividing the work between each process. So it's basically on us, the programmers, to figure out how to write parallel code. It's way easier if you have the compiler just do it all for us, but in the case of OpenMP, we had to recognize that our for loop. In the case of OpenMP, we had to recognize that we had a for loop where we can make it parallel. It doesn't work for all types of for loops, so we have to recognize. So we have to recognize that this specific for loop can be made parallel. We add in that parallel. We add in that parallel for directive right before the for loop, and then the compiler just does all the magic for us. So really, there kinda is a third category where we recognize that there are sections of code that can't be made parallel, and we tell the compiler, hey, make this section of code parallel for me. So OpenMP is kinda in between these two extremes, where the compiler does everything for us and we have to do everything ourselves. Alright, so I want to get into the modes of distributed execution. And there are 5 main modes for this. The first one is single instruction, single data. So, standard sequential program, no parallelism whatsoever. Most of the programs you've ever written in your undergrad will most likely be under this category. Even down to the Hello World programs. Because if you think about it, you can simulate a Hello World program on a Turing machine, and I'll just simply print out all the symbols one by one. Alright, so that's SISD. Next, we have SIMD. Same instructions on different data, or single instruction, multiple data. Well, this is exactly what we did with OpenMP. We had a lot of data, but we wanted to use the same exact set of instructions on it. Single instruction, multiple data. So we're doing the same thing on a lot of data. This is also the basis of all sorts of GPU computing, where you have the same operation being done over and over again. It's a bit of a tangent. For my master's project, I'm actually looking at ways of using text generation to train a neural network for another thing. So what I'm doing is feeding text from a neural network. No, what I'm doing is training a neural network to train another neural network. One neural network generates text that the other neural network is gonna try to label. It's a bit convoluted having neural networks outputs feeding into the input of another neural network, but this is a setup that's not unheard of when you're looking at data science. Since there are neural network pairs that have to work with one another, generative adversarial networks generally have two neural networks that have to compete against one another. The best way to describe it is, if one network, this is for generative adversarial networks, if one network is a counterfeiter, the other network is trying to detect the counterfeits. The ultimate goal is to have the counterfeiter make extremely convincing counterfeits. So yeah, that's one situation where you want to have a neural network have its output be the input of another neural network. Speaking of neural networks, a lot of neural networks, they're basically lots and lots of linear algebra, specifically matrix multiplication and matrix vector multiplication. And all of that is just a whole bunch of repeated additions and multiplications. By that, give me a second. I'm just gonna quickly pull up a Wikipedia page to help me illustrate this thing. So, this is basically the layout for matrix multiplication. You have a matrix of size L by M multiplied by a matrix of size M by N, and you get another matrix of size L by N. This is how you compute it. You see this row here? If we treat that as a vector, and we multiply it by this column here. If we multiply this vector with this vector, it's basically this times this, plus this times this, plus this times this, and that entire sum goes here. And then we repeat. Maybe it's way better if I demonstrate with a pen. Give me a minute. Okay, I'm back. So, to get this result here, let's call it A. Let's call it C1. No, let's call it C11. We'll call this A11, A12, A13, B11, B21, B31. So what's this? So what is C11 here? Well, it's A11 times B11 plus A12 times B21 plus A13 times B31. Or another way to put it is to say that we're multiplying this row vector with this column vector. So let's call this C1. No. Let's call this R1 and this C1. So C11 here is actually row vector 1 times column vector 1. And then we just repeat this entire process for this element, here, and we just keep going. So yeah, it's every possible multiplication between row vectors and column vectors, and that populates the resulting matrix, and all of that is just additions and multiplications with the same numbers. Nothing in these numbers no number in here is ever being changed. So in theory, we can calculate all of these products at the same time. And that's what GPUs do. Or rather, that's what a lot of data science does. And because of that, it's often the case that when you're doing data science or you're using neural networks for anything, you're gonna want to compute this on a GPU, because a GPU has way more cores than a comparable CPU. I've shown my computer stats already. It's a Ryzen 7 1700 8-core processor, and my computer also has an NVIDIA GTX 1070. If we look at the number of CUDA cores on this thing, we get, 1900 CUDA cores? So that's 1900 cores on which we can do all sorts of parallel computing, compared to the 8 or rather 16 threads that my computer currently has. But another note is my CPU runs at a higher clock speed than my graphics card, but that's okay. What matters more is that we're doing a lot more computation per unit time, just by having way more cores than just the CPU. I think that's enough of a tangent already. So yeah, so a lot of data science is contingent on using GPUs simply because they're just way faster than a regular CPU. And we can do that because we can parallelize the hell out of this. Right, continuing on. multiple instructions, single data. So different code being done on the same data. So imagine you had a data set and you wanted to do different things to it, but each different thing is being done by a separate program. That's what it kind of sounds like. Another way to think about it is, imagine you're traversing a maze, or rather, you have a computer that's trying to traverse through a graph, and you want to find, say, the exit to that graph. So you have a start point in the graph and then an end point, and you want to find the exit, but you want to explore that entire graph to see if there's a optimal exit, or rather, a good enough exit. So basically, this is a weighted graph where it takes some time to traverse each connection between nodes. And what if you hit a dead end? You're gonna want to backtrack, go to a previous node that had like branching paths, turn around, and go back on that other path. So that's more of what MISD does. Multiple instruction, multiple data. So this is the most general model of all, communicating different processes with different data. Yeah, this is the most general model of all. So it's like, and it's kind of like this. It's, if you think about it, it's a little bit like the client-server model, where you have computers coming in and out. No, computers coming and going, connecting to a server, and then disconnecting from a server when they're done. Each computer connected is doing something else on some other data. It's like if you wanted to play Minecraft on one computer, but you also wanted to do data science on another computer, which is what I've done. Actually, no, that's a terrible example. That's a terrible example because none of the computers are talking to one another. I guess a better example would be if you had to set up a Minecraft server on a local area network, but you had one other computer on the same network that's somehow doing data science. It's an interesting thing that they brought up Minecraft, but you'll see why later on. Now, there is a fifth model, and that's single program multiple data. A single program has the code to do all sorts of different tasks, but copies of that program will only ever do just one task. But it has the effect of having multiple programs doing different things on different data. So, this is a setup where you have one program with different tasks. And this is task parallelism. What is task parallelism? Well, imagine dividing up the work of a video game. So a video game will have different things going on just to work. You can have the physics engine doing collisions between objects and the ground. You have to simulate them falling. You have to simulate collisions. You have the sound engine, which has to listen to events and play out the appropriate sound. So if something hits the ground, the sound engine has to recognize that event and play the appropriate sound. If it's an online game, you have to have something listening to network traffic and sending out network, and it has to listen to packets and then send out packets. If there is a game loop, that you also have to deal with that. And if you have graphics, generally you're gonna need something to deal with graphics. So you can imagine all these tasks happening all at once. And if the game is multi-threaded, you could delegate each task to each thread. So this is kind of like SIMD and MIMD because of the overlap, but this is way more practical than just MIMD alone. So I will say right now that both OpenMP and MPI are capable of SPMD, and that's because we can specify different tasks in the code to do different things. That's exactly what we did with that's exactly what we did with the OpenMP sieve. Actually, no, not the OpenMP sieve, the MPI sieve. We had rank 0 simply doing the work of sending and receiving data to all the other processes and then updating the data to be sent again. All the other processes are, actually doing work. So yeah, we can do SPMD using MPI and OpenMP. So I guess here's another question we can bring up. Can we use parallel programming for brute force? I'll give you a minute to think about that. So what do I mean by brute force? Well, suppose you wanted to play a Sudoku puzzle. The rules of the game are simple. Each 3x3 box has to have all the numbers from 1 to 9 occurring once. Each row also needs to have 1 through 9 occurring once, and each row has to have 1 through 9 occurring once, and each column has to have 1 through 9 occurring once. Now, what's one way you can solve this? Well, we can just put in random numbers and see if they work. So if I put in a 1, it doesn't work because there's already a 1 here. So we cannot put a 1 in here. So let's erase that. One way I like to solve this Sudoku puzzles, by the way, is to deduce where a number cannot go. So, if we have this 1 here, we can just take a glance and determine that a 1 cannot go here or here, but it can go here and here. But here's an interesting thing. If we have all these 1s here, we cannot have a 1 here, so it must be restricted in this row of 3 1s here. But it doesn't matter. But look at this look at this pair of 2 possible locations where a 1 can go, because a 1 can appear here and here and here, any one of those locations. It doesn't matter where we put it because it's gonna say, hey, we cannot have a 1 here. So that eliminates the possibilities. So we must have a 1, not there, but point. You must have a 1 here. Right back. So how does the computer solve Sudoku puzzles? Well, it turns out they solve it through brute force. They just determine what numbers can't go and they just determine what numbers are already used, and they just put a number in a location, try to solve it based on that, and if they run into a problem where they have a number occurring twice in a row or column or 3x3 box, they're just gonna undo all that progress and try a different number and then try again. So basically, Sudoku puzzles aren't solved by computers the same way we would solve a Sudoku puzzle. Oh, and by the way, 1, 2, 3, 4, 5, 6, 7, 8. This number here is a 9 because there's literally no other option. So yeah, brute force. What else can we use brute force for? Well, I do have a video here, and I think I'm just gonna post a link on Canvas for this. But if you've ever looked at Minecraft for... If you ever looked at Minecraft for its odd programming projects, this is one of them. The quest for the tallest cactus in Minecraft is a fun example of using brute force and parallel programming just to find the tallest possible cactus in the game. The thing about Minecraft is, well, I'll just show you. A lot of Minecraft has changed over the years, so what happened in one version cannot happen in another version anymore, unless you change versions. But we're currently at version 1.19, and this video actually talks about 1.12 to 1.15, I believe. So yeah, lots of changes to Minecraft, so a lot of terrain generation features might not really work anymore. So what I want you to do before we continue this video is to watch, or you can just watch this video at your own time. What I'm going to do is get into an example where we want to find the seed for a random number generator. Okay, now we're back in Visual Studio, and I want to show an example of what do I mean by finding the seed for a random number generator. Right, so there's one way of making a random number generator in C++, and that is using, srand time null. There's another way, and that's by coding it like this. Let me show you. We have to import the, we have to include the random library, and this is what it looks like. First, we need to create we have to make what's known as an engine. So, standard, we can just use the default engine for this, so default, random engine, and then you have to pass in a seed. Because the thing of most random number generators we ever deal with in computing are of the deterministic variety. By that I mean, you have to give it a number with which to initialize the random number generator, and that goes into a special function that hopefully produces adequately random numbers for our purposes. This is either a good thing or a bad thing, depending on how random you want things to be. Because there are some situations where you cannot want the seed to ever be found. On the other hand, there are situations like Minecraft where you want to share the seed. Anyway, we can initialize the seed as being times 0. And we're not quite done yet. The next thing we want to do is to create our random number generator itself. So, standard, and we want, a little bit of probability and statistics. Actually, I have a more fun example right here. So what we want is what's called a uniform distribution. So, but we want integer values. So we want uniform int distribution, type of int, and then we say RNG 1, comma, let's do 20. So what's a uniform distribution? So if you roll a 6-sided die like one of this, or even a 20-sided die like this, there is an equal probability of, let me rephrase it. Every number on this die will have the same probability of coming up. And that's what we mean by and this is what we mean by a uniform distribution. Every possible outcome has the same chance compared to one another. So this one, for example, each number from 1 to 4 has a 25% chance of coming up. And awkwardly, you have to read the tip and not the bottom. Anyway, so we basically have a simulator for rolling a d20. Okay, so let's try this out and let's roll our d20, say 5 times. And to get a value, we have to also see out it. Let me just see out it. So standard see out, and then what I want to write in is RNG, and then we pass in the engine as a parameter. Alright, so we're gonna roll our d20 5 times, so. And if we press F5, there we go. It rolled our d20 5 times, and now we have numbers 6, 20, 18, 15, and 1. There we go. Now this engine will take in a parameter that's our seed, so let's just pass in a seed that's pretty simple. So 1, 2, 3, 4, 5. Actually no, 1, 2, 3, 4. That's a good seed. Good seed, but a terrible password actually. Alright, so let's try this. 16, 12, 7, 6, and 17. And if we try it again, we get the same numbers. Alright, so this engine here will take in a seed. We have it be times 0 if we want a random seed, so that whenever we rerun the program, it'll produce new random numbers each time. But if we want to lock it to a specific output, that is to say, if we found a seed that is ultimately used to produce a specific sequence of numbers that we want to save, so we can, say, share to a friend, we want to know that seed. But what happens if we forgot the seed? Is it possible to find the seed again? Well, in this contrived, super duper simple example, the answer is yes, we can. It gets harder if you're trying to find a seed for a video game that's based off of procedural generation, aka Minecraft. In fact, as another tangent, there was an effort to find the seed for a Minecraft world, but all they had to go off of was a 128 by 128 image. So yeah, 8 months of work just to find the seed. So yeah, anyway. And by the way, there is a video for that too, and it is related to the cactus video that I showed in the PowerPoint presentation. So yeah, maybe I'll just show that. Maybe I'll just show what. Yeah, maybe I'll just talk about that later on. So anyway, let's get back to our example. So we know that our numbers are 16, 12, 7, 6, and 17. Let's pretend for a moment that we forgot the seed was 1, 2, 3, 4. So, can we brute force a seed? Sure. What we need to do is try out every possible number from 0 to the maximum integer value as a seed for this engine, and then have that output a sequence of 5 dice rolls, and if it matches the sequence that we started with, then we found our seed. What I'm going to do is I'm going to store the numbers that we found in a vector. So numbers were 16, 12, 7, 6, 17. Maybe I should just zoom in just in case. And now we want to make a for loop. I guess less than. Okay, let's pretend for the sake of demonstration that we forgot what the seed was, but we do know it was a 4-digit seed. So let's search up to 10,000. Right, so int seed equals I. We want our default random engine again. By the way, if you use a different engine, this might not work. So the stipulation is, we knew that the seed was a 4-digit number, and we know that we're using the default random engine. So oh, by the way, you can do this with srand time null, and it'll still work. I'm just using it with the random library because that is one of the new features of C++ that I want to show off. Anyway. Okay, so there are actually 3 stipulations. We knew that our seed was a 4-digit seed. We know we were using the default random engine on a uniform integer distribution, and we know that the numbers were between 1 and 20. And we have the numbers that it originally generated. So what we want to do is we want this test random number generator to generate 5 numbers and store those in a vector. So the way we generate random number generators is we take this uniform integer distribution, and we pass it the engine as a parameter, and it will generate a number, it will return a number, and then we just push it back at the end of the vector. And so that's how we're storing all of our numbers. So we want to find our 5 numbers, and then we want to compare it with the numbers that we already know, which are here. So we want another for loop. But we also want a bool out here. So this bool says, did we find the seed? We've initialized it to true, and then we compare these 5 numbers in here, with the 5 numbers that we stored in here. So, seed found ampersand equals so we're just gonna go element by element, comparing the first number with the first number in the sequence we generated, and we keep going for the next 4 numbers after that. If all 5 numbers match up, then we have found the seed. Random numbers I equals test numbers I. And then we found the seed, we print it. Alright, so, again, let's pretend that we forgot what the seed was. But we do know that using this specific configuration of a random number generator, we know that we had these 5 dice rolls. So, let's run the program. There you go, we found the seed. It was seed 1, 2, 3, 4. So we magically forgot that it was 1, 2, 3, 4. We did a brute force algorithm here to find what it was, and we found it. 1, 2, 3, 4. So here's another question. Can we, since we're here toying with this, can we have it find an arbitrary sequence of numbers? So 7, 12, 16, 17, 1, and 13. Will it find a seed? Is there a seed that corresponds to these random numbers? No. What if we increased our search range? No. What if we could keep expanding our search range? Okay, it found 1 seed that satisfied the sequence of random numbers, but it's taking quite a bit. Do you see where parallel programming might save the day for us? Remember in OpenMP we had a for loop that we made parallel? So the idea is, what if we brought in the help of OpenMP and made this for loop parallel? Our next assignment is literally to try this out for ourselves and brute force and to brute force the seed for a sequence of numbers. That assignment is, the due date for that assignment is to be determined, but what I'm doing right now is I'm showing you the working principles of how we go about finding such a seed that satisfies a specific sequence of numbers. And here's the weird thing too. It's finding multiple seeds. Yeah, so here's the thing. There may be more than one seed that satisfies the condition of having this specific set of numbers being generated in sequence. So I'm just gonna do a quick search and while that is running, I'm not gonna play these, but they're pretty easy to search up. One of them is the Minecraft title screen seed. I'll just summarize what the video was. Basically, in many versions of Minecraft, there was this title screen image of a Minecraft world, and the idea was, let's find the seed for that world. And they did. They found the seed for it, but here's the weird part. There were two seeds. There were two seeds that generated the same exact world as shown in the Minecraft title screen. So yeah, sometimes you might encounter more than one seed that satisfies the same exact condition. So, if you're curious as to how all of this works, there's a series of videos by the YouTuber SalC1, who basically talked about how they found the seed for a 128 by 128 image in Minecraft. That is also a really interesting application of parallel programming and brute force. Again, I want to explore more of the fun and interesting applications for parallel programming rather than just delve too long on the theory, and that's why it's done. And that's why I wanted to focus more on, for now, this is why I want to focus on using brute force to find the seed for a random number generator. In fact, this was the inspiration for this upcoming assignment. Due date is to be determined because currently you have a midterm project whose due date I actually pushed back by request to be on the 24th instead. So for those of you who were worried that you'd run out of time for your midterm benchmarkings, I pushed back the due date to the 24th. So you still have some time. Alright, so I guess that's going to be it for today's video. If you have any questions or issues that you want to bring up regarding your benchmarks, let me know. And I'll see you next week.